See, basically, when we talk about the transistor, transistor is a three-terminal device, right? There are three terminals. One terminal is emitter, one terminal is emitter, another terminal is base, and another terminal is collector, right? There is three-terminal device. This is a three-terminal device. So basically, if I talk about the transistor, this emitter is used to inject. Do you know there is a two types of carrier inside the semiconductor, that is majority charge carrier and another one is minority carriers? Hello, right. So this is a p type semiconductor. Inside the p type semiconductor, what are the majority charge carrier? Holes. And inside the n type semiconductor, that will be electrons, negative, right? So basically what is happening inside the transistor, the holes the holes which are coming from this emitter, this region is called as emitter region, right? This smaller region inside this one, that is called as base region, and this third region is called as collector region. So basically if I'm talking about the area, the base is narrowing. You can say the base is the having the smallest width. Base is having smallest width, collector having highest width, and the emitter having moderate width. Remember that thing. He will bring the question in MCQ from this one, right? Or not MCQ, true false, right? I think I remember the last year I taught the Latifa and Manal, and he bring this question that which one having the smaller width, that is base, right, Gala? So the base is having, just just record this lesson if you want to listen it later, right? That will be easy for you to, the audio is not recorded, okay? So basically what I told you, that the which one has the smaller width, that is base. Which one has the highest width, that is collector, and emitter has the moderate, right? Very good. So now what is happening inside this transistor, let us take this is the holes are the majority carrier here. So these holes are start going to the base region. Let us take 1,000 holes are starting from the emitter terminal and they will enter to the base. So inside the base there are some electrons that are majority charge carrier. So some of the holes will recombine with these electrons, right? And let us take 10 electrons are 10 holes recombined with the electron. So how many holes will reaches to this collector? Can you tell me? There is 1,000 holes which are coming from this emitter. 10, let us take note, 10 100 holes recombined in the base. So how many will reaches to the collector? That is 900, right, Gala? Should I repeat this thing again? Right, because this there is a recombination. It means what is happening. So basically the 1,000 hole coming from the emitter, 100 holes recombined in the base, 900 holes are reaches to the collector. So that's why what we are trying to do, we are trying to maintain this width smaller so that there is less number of recombination, so that your collector current is almost equals to the emitter current, right? So basically what is happening, the emitter current is how much? That is 1,000, right, Gala? And that will be equals to what? IB plus IC. This is our first relation. Did you understand or not? Because there is a thousand holes are coming from the emitter and 100 recombined in the base. So the base current is due to this recombination of holes, and this the rest 900 will reaches to the collector. So your collector current is due to this holes which are reaches to the collector. So always remember the emitter current is high, you can say the bigger one, base current is smaller one, and collector current is moderate. Should I repeat this thing again or you understand? Yes. So which current is bigger if I'm talking about the current? Which current is bigger? IE. And yeah, yes, because that is 1000. Just remember this example: 1000, 100, and 900, right? So emitter current is highest. Then which current will come after emitter current? Then IC and then IB. So this will be the order. I will show you. I solved one exam last week for this one. Right, in that one MCQ, I have that true and false that will come from here. We will discuss it later, right? Don't worry. Okay, so that is the basic thing about this transistor. Understood? The transistors are two types. That one is PNP, another one is NPN. Right, Gala? So what is the meaning of PNP and NPN? See, basically how we can decide that this is the symbol of a transistor. How you will decide that this is PNP or NPN? Did you see this symbol? How you decide this is a PNP or NPN transistor? Can you tell me? Okay. So basically, always remember where the arrow is that this arrow represents the it. This arrow represents the. Okay. Before moving to this one, just to tell me one thing. This is P type. This in between N type. Then we have P types. So there is how many PN junctions? Can you tell me, Gala? How many PN junctions are there? Two PN junction. PN junction means where P type and N type semiconductor will meet each other. And this first PN junction represents emitter base junction. Right, Gala? The second PN junction represents collector base junction. So there are three PN junctions, sorry, two PN junctions inside this one. So basically, what we are seeing, this first PN junction can be worked like a diode, because inside the diode we have two regions, P regions and N regions, right? Like this. And current is flowing in which direction? Can you tell me? Inside the diode. The current is always following from P to N. P to N. So basically current is always flowing from P to N. So same thing is happening here. What you are seeing, this junction, this is represents what? This always represents base, this emitter. So this arrow is always available at the base emitter junction, and this is our collector here, right, Gala? So these are the three terminal. Always remember this arrow. This arrow is always in between base and emitter, right? The third terminal is going to be collector here. So from this direction, yeah, just give me 1 minute, Gala, I will back just once. Right, right, Gala. So back here. So what we are seeing, there are two PN junction, that is P and N. Back here, see, basically this is base, this is emitter. This arrow represents the current following. So current is always following from P to N. So this is P side, this is N side. So the remaining will be N. So how we can decide? Did you understand this is PNP transistor and PN transistor or not? See, if this arrow, if I put this arrow in the inside direction, so what is happening? Can you tell me? Like this. This is base, this is emitter, this will be collector. So which type of transistor is this one? Are you there? Gala, are you there?
Just a
or
minute,
not?
just a minute.
Okay. When you are ready, just tell me, I will start.
Yes, I'm with you.
Right. So what is happening here? This arrow is like this. So it means which side is p type? Can you tell me? This emitter side is p type, and this base type is n type. That's why this current is going from p to n. Understood? So this arrow
So,
represents the direction of current,
so
and
I have
that
a
will be,
question.
yes, please.
Yeah, yeah. I was just asking about the C. Is it P or N? Because it looks like a. It doesn't look like the E. So I was confused if this was P or N.
So this is okay. Okay. See, basically, this is the symbol for transistor. First thing, this is the symbol for transistor, which we generally use. Got Kala? This is the
Yes.
symbol just. Okay. So inside these symbols, we put one arrow. Either the arrow look like this one, or either the arrow is
The
going
other one.
up,
Yes.
right? Like this. So first thing we have to decide that which one is base, which one is emitter, which one is collector. There are three terminals: emitter, base, and collector. Right,
Yes.
Gala? So the
Yes.
first we have to decide the base. So always remember this arrow. This arrow is in between base and emitter.
Okay.
So this line represents the base. This line. Always remember this is your base and this is your emitter. Got my point or not?
Yes. Yes.
And the remaining terminal, the third terminal will be what? That is
The C.
collector.
Correct.
Collector. Did you understand this one or
Yes.
not?
Yes. Got it.
Now we have to decide that it is a PNP type or NPN type. Right? PNP means what? See, this is your transistor. PNP means P, N, and P. Your base is N type, emitter is P type, collector is P type. Another one is NPN, N, P, and N. Your base is P type, emitter and collector are N type.
Yes.
Got my point or not? So now we have to decide that which transistor represent NPN or which transistor represent PNP. So basically, this arrow represents the direction of current. Right, Gala? And the
Yes.
current is always flowing from positive to negative, means P to N. So it means your base terminal is what? P type. And
P type
emitter terminal is N type.
and type and the
Understood?
C. Yes. Yes.
N type, because NPN, either NPN or either PNP, because emitter and collector remain the same type. Can you see here? Either P type, either N type. Understood or no? Tell me now.
Yes.
On the last one is which type of transistor is this one? Because arrow is going inside, right, Gala?
Yes. It's the
Arrow,
other way.
the other one. So the emitter is P type, base is N type,
And
and
type and
collector
the
is
C is P.
P. Understood how we can decide the type of transistor, which type of transistor is this one or no? Tell me now.
Yes.
Okay. Next thing. So this is the basic of the transistor. Okay. Next thing, your transistor will be operated in three regions. Yeah, one more thing. See, basically, inside this transistor, can you tell me the direction of currents? See here, Gala, this is emitter current. It is always greater than. So you remember this relation. Emitter current is equals to IC plus
IB.
IB.
IC. IB. Yes.
So basically, IE current is emitter current because the direction of current is this one. So emitter current is going down. It means this IE current is equals to what? IB. So this IB current is going inside, and this IC current is also going inside. That's why your IE current is going out in this transistor. Did you understand this one or not?
Yes.
On the other transistor, because the arrow is in this direction, so it means IE current will enter inside the transistor, and IB current is going out, and IC current is going out. So remember this direction of the current. This is the direction of the current. Understood?
Yes.
This is really important. You can take the screenshot of this one, right, Vala?
Yes. I already took.
Okay, one more thing. See, basically this transistor is operated in three regions. This transistor is operated in three regions. So what I taught you, that there are two junctions or not? We
Yes.
already discussed this one. Is done. Yeah, there are how many junctions? Inside the transistor, there are two junctions. The first junction is what?
The P.
Emitter base junction, right? The second junction is collector base junction, right?
Yes.
Can you tell me how when your PN junction is forward bias and when it will be reverse bias? What is the condition?
So when the
We have a
it's
diode,
from the we have a diode from the positive to the negative, P to N, and the
right?
reverse is the other way.
See, basically, whenever you decide that the diode is forward bias or reverse bias, we have to check the potential at the voltage at P terminal and voltage at N terminal. Right, Kala? If your voltage at P terminal is greater than voltage at N terminal, right, then you can say the diode will be forward bias. If it is an ideal diode. And if your Vp is less than Vn, then your diode will be reverse bias. These are the two conditions of the diode. Okay?
Okay.
You should remember that one, right? Okay, back here. So basically, inside these two junctions are there. So basically, first junction is emitter base junction. The second one is collector base junction. So if your both the junctions are forward bias, both the junctions are forward bias, right, Kala? When your both the junctions are forward bias, then your transistor will be in saturation. In which region? Saturation region. What are the conditions for saturation region? Your both the junction, emitter base junction and collector base junction, both the junctions should be forward bias. Understood?
Yes.
Second one is active region. Remember that in active region, your emitter base junction is forward bias, collector base junction is reverse bias. I will tell you how we can perform that one, right? Just memorize this table. It is so important. You can say almost 2 to 3 questions in true false you get from this table, right? And the last one is cutoff region. Cutoff region means what? When your both the junction, emitter base junction and collector base junction are reverse bias. Right, Kala? Then we can say that is a cutoff region. So this is most important table. Okay, Kala. Can you see this structure? The one second. This structure.
Yes.
Can you tell me this emitter base junction is forward bias or reverse bias? Just tell me that one.
Forward bias.
Forward bias. And this collector base junction?
Also forward bias.
No. Can you see here? This n-type material through this battery. This n-type material is connected to the positive of battery or not?
Yes.
And this p-type material is connected to the negative of the battery?
Also reverse bias.
Reverse bias. So which mode this transistor is working? This is reverse bias, this is forward bias. Can you tell me in which mode this will
Active.
work?
Active region.
Active mode. Active region. Understood? How we can
Yes.
decide this in which region it will work? You have to check this thing. Can you tell me this one? The second case?
So the N is with
Second
the
case.
positive. So this is the reverse bias, and the other way N is with the negative. This is forward bias. This is also active region.
Very good. So you understand how you can decide the reason or not? Tell me that one.
Yes.
So remember this one. This table is really important. ये ले जाओगे बांट दोगे नीचे मैं उठा लूंगा इसमें है पानी अभी कितना so these are the region of operation of the transistor. I already discussed these symbols with you, how the current
Yes.
will flow and everything, right?
Yeah.
We covered here this one. One more thing. So basically your transistor can be operated in three configuration. The transistor is operated in three configuration. Common base, right Kala? Another one is common emitter and common collector. So first let us discuss what is common base. What is the meaning of common base? See, basically inside the transistor, if I take the transistor like this, so can you tell me which terminal is this? Let us take current is going out like this. Which terminal is base, which one is collector, which one is emitter? Can you tell me inside this transistor?
So this one is base.
Lower one, right?
Yeah. This one, and the other one is
Okay,
the emitter, the next to the arrow.
right. And this
And
one is
yeah, this is the common.
collector. Collector. So
Oh, sorry,
basically
common.
inside this one, what I did, yes. Inside this one, what I did, this is our RE resistance and we provide the input here at this terminal. Right, Kala? So this is your VBE, base to emitter voltage, right? And we are taking the output at the collector terminal, right?
Okay.
And that is VCB voltage, right, Kala? So this is RC resistance and IC current is going here. Sorry, the direction is not correct. Because which in which direction the IE current will flow? The IE current is going in this direction, right, Gala? So it means
Yes.
if I is going in this direction, IB will coming in, and this IC is also coming in like this. Understood this thing or not? Tell me. This
Yes.
structure you understand? So what
Yes.
is happening? Which we are taking the output at the collector and we are giving the input at the emitter. So in between input and output, which terminal is common? That is base. Can you see? The base terminal, this base terminal is common in between input and output or not? Tell me that thing.
It is.
It is. So that's why it is called as common base configuration. Right? Why we are saying say this that it is a common base configuration? Because your base terminal is common in between input and output. Because this VB voltage is called as input voltage, and we are taking this one as a output
Output.
voltage. Did you understand everything? That why we are saying this is as a common base?
Yes.
Okay. So inside the common base, if I want to draw the input characteristics means what? We have to take the input voltage on the x-axis. So input voltage is what? VBE. And output current is, sorry, input current is how much? That is IE. So this is input characteristic. Did you understand or not? Tell me that thing, Ghala.
Yes.
Should I repeat it again or you understand that thing? If I draw the
No,
input characteristics, so in input characteristic in this configuration will be with respect to IE and VBE. And output characteristics are what? Can you tell me? The output current and output voltage. So the output
VCB.
current is IC and
IC and
VCB.
VBS.
VCB. Understood, Gala, or not?
Yes.
Back here. So this is your input characteristic. Can you see IE and the other one is VBE, right? You can see, check here, input characteristic for common base configuration. And one more thing, do you know the diode characteristics or you don't know that one? The diode characteristics in forward bias. The diode characteristics, you apply the voltage here, that will be ID. Your diode characteristics look like this one or not?
Yes, in the forward bias.
In the forward bias. So what we are seeing here, this junction, this emitter base junction is forward bias. I already told you in active region, your emitter base junction is forward bias, collector base junction will be reverse bias. So we basically this PN junction is forward bias. That's why this input characteristics are look like this one. Did you see, Gala, or not? These are the diode characteristics. You can see that one here. These are the practical cases, you can say. So what we are seeing, these are the input characteristics of a transistor, which is similar to the diode. Understood or not?
Yes.
Should I explain this one or you understand everything till now?
No, I got it.
Yes. And after how much voltage they will start increasing like this? Do you remember in the diode? That is 0.7. That's why these are increasing after 0.7, that will fastly. Right? So generally in this case, the VB, base to emitter voltage, generally replaced by 0.7 volt inside the transistor. We will do it later. Don't worry. Okay. Next one is output characteristics. So I already told you that there is output characteristics of the transistor. So which current I have to take
I see.
and which voltage I have to take?
VCB.
VCB. So basically these characteristics of the transistor are called as output characteristics. Right? In case of which configuration?
The common base.
Common base configuration. Very good. So in common base configuration, this current is IB. So basically what is happening here, I will tell you that. See, this is our characteristics for fixed value of IB. See, this is our first characteristics when your IE is equals, not IB, sorry, IE. Input current. Always remember this is the input current here. This is IE is the input current, right? For
Yes.
everything. So basically, this is your output current for a fixed value of IE. When your IE is equals to 1 milliampere, when you increase the IE value, this IC current will also increase like this. So when you increase the IE, this value current increase. So inside this characteristics, always remember there are three regions. The first region, when your IC current is zero, this region, in which region your IC current is zero. Can you see here, Gala? Let me check it.
The cutoff.
When your IC current is zero, this region, the red one. Yes, that is cutoff region, because inside the cutoff region, what happened? Both the junctions are reverse bias. Inside the reverse bias, there will be no current will
Yes.
flow, right? So that's why we can say inside the reverse bias region, one second, I go to my message. Right? So this is the cutoff region. Always remember when your current is linearly increasing like this, right? Linearly increasing like this. So that region is represents what? Saturation region. This is your saturation region. Always remember. And the rest of the region from here to here, that is active region.
Okay.
Right? So there are three regions inside this one. So basically, if I give you this characteristic, output characteristic, from this output characteristics, right? From this output characteristics, can you tell me that which configuration is this one?
Which one?
How you can decide that which configuration? See, I give you this output characteristics, and you have to tell me that which configuration.
So basically, when it's
So how you can decide
aligned,
that?
when it's aligned, it's a cutoff region because both are reverse bias, so that there is no
Right.
current. And when it's increasing,
No, I'm asking. Yeah, I understood. You can tell the
yeah,
reasons, right? Like
yeah,
this which
yeah.
region. I'm talking about the configuration. That is three configuration. That is common base configuration, common emitter, and common collector. So how you can decide this is a common base, common emitter, or common collector, right? How you can decide that? So always remember this current. This current is input current, right, Gala? And this
Yes,
current is output current. So we know that this is input current and this is our
out.
output current. So which one is left in between these three currents? See, this is the emitter current. Can you see here, Gala? This
Yes.
IE is the emitter current, and this is IC. That is a collector current.
Yeah, we still
So
have the IB
it
left.
means which current is left? That is base current. So that base current is common in between these two. IB left. So that's why these characteristics are representing what? The common base configuration. Did you understand what I told you?
Yeah, so I look for the input and the output, and what's not there is basically the configuration.
Yes. Yeah, that will be common. Like this. Come
Yeah,
here.
yeah, in this case.
This con. Oh, don't know this case. Yeah. See here. This current is what? This is always
IB.
remember. This is the input current,
Yeah, that's
right?
acts as
Input
the
current. That
input.
is IB.
Yeah, yeah. And IC
And
is
this
the
one is.
output. So I emitter is
So which one is
the
left?
emitter current. So common emitter
Emitter current is left. So
configuration.
which configuration? Very good. Understood this one? Again,
Yes.
a third case. This is. Oh, this is the same question. We will do it later. Yeah, tell me. This is the configuration. Yeah, this is the third configuration. What you are seeing, IB is here and IE is here, right? This is your input, right, Gala? And this is
Yeah.
our output.
Output.
So which terminal is
The
which current
IC.
is left?
IC.
So that means it is
The um the collector.
common collector.
Yeah.
Yes. So now move to your example. One question you send it to me. Once again. Yeah. Can you tell me which configuration is this one? He is asking this one.
So input is IB, output is IC. We still have the common base.
Check it again.
Is
Input is
IB,
IB,
the output IC,
output is IC.
sorry, the emitter.
Yes. So this is common emitter configuration, right?
Yes.
Why it is common emitter configuration? Because your input is given at the base terminal and output is taken at the collector terminal. So that means it is a common emitter configuration because he is asking for why. So you have to write that because the input is given at the base terminal, output is taken at the collector terminal. So the gate terminal will be, emitter terminal will be common in between these two. So that's why this is a common emitter configuration. Right, Kala? Understood that thing or not?
Yes.
Or should I repeat it again?
I got it.
Yeah, back here. So basically come to the first point. Okay. Yeah. Not this one. We are here. Yes. So these are the output characteristic, input characteristic. Did you understand both of them or not? Tell me.
Yes.
And this is your common base configuration. Right. I already told you that inside the active region, the active region base emitter junction is forward bias, and whereas the collector base junction is reverse bias.
Reverse
I
bias.
already told you these things from the table, if you remember, right?
Yes. Yes.
Cutoff means both the junctions are reverse bias.
Yeah. Both are reverse bias, and the
And
saturation,
saturation means
forward bias, forward bias.
very good. Can you check it here? Right? It is written. I already discussed everything with you. Okay. One more thing. Back here. This configuration is what? Common.
Common base.
So what is the output current? What is the
The
output current of this IC?
IC, yes.
The out and input current is what?
Uh,
Can you tell me? What is the input current?
I emitter. Sorry, the VBE.
Just remember, Gala, we are giving the input to this terminal. This is our input. So this current, input current, right? We are taking the output at here. This IC current will be output current. Understood or not? This is your input terminal. Let me make it with black. That will be visible to you. This one. This is your input terminal, and this one are output terminal. Right, Gala? So
Yes.
this current IE is input current, and this IC current is the output current. Got my point?
Yes.
My voice is clear to you or not?
Yes. Yes.
So basically, the output current is IC and input current is IE.
I.
So if I divide the output current upon input current, right? So that will represent the current gain that is represented by alpha. So alpha represents what?
IC over IE, so it's the
Common base.
common base configuration.
Yes. Common base current gain. So this alpha represents common base current gain. And always remember this value is IC upon IE. So what you are seeing here, the alpha is going to be how much? If you remember, I already told you that IE is equals to 1000, then your IC is equals to how much? That will be 900, and IB is equals to how much? Do you remember that? That is the 100. Right,
Yes.
right, Gala?
Yes.
In the
IE
starting.
equals to,
So basically,
yeah,
what
IC
we are
plus
seeing
IB.
that IC plus IB. So basically, IC is always less than IE or not?
Yes. IC is less than IE.
IC is very good. So it means this value is always less than 1 or not? Tell me that thing. Because numerator is lesser than the denominator. It means if you take an example 9 divided by 10,
Yes.
that means 0.9. That is less than 1 or not?
Yes.
So remember, alpha value is always less than 1. Right? Less than or equals to 1. So basically, in ideal case, alpha is almost equals to 1. If I talk about the practical case, alpha value generally lies between 9.5 to 0.99. This alpha.
Okay.
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 And what is the alpha? That is IC upon IE. remember. And this is called common base current gain. Can you see here? And that is lying between 0.9 to 0.998. Okay, Gala? Any doubt in
Okay.
this one? Then please ask.
No, it's good.
Right. So this is the configuration is given to you. Let's do this question fastly. So using the characteristic, determine the resultant current if IE is equals to 3 milliampere and VCB is equals to 10 volt. Can you tell me how can we can do this? Any
So
idea?
he wants the alpha or he wants IC, right?
Can you read this question? Yeah, he is asking for IC.
So we will use the formula IC equals IE equals IC plus IB, right?
No, no. Gala here. This is from output characteristics. We have to calculate it from the characteristics. Now I will teach you that how we can calculate from the characteristics. Okay, Gala? See here. Determine the resultant collector current, right? We have to find IC, value of IC, right? From these characteristics. When
Yes.
your IE current is 3 milliampere. So first check the IE current is 1 milliampere here, 2 milliampere here, 3 milliampere here. Can you see here, Gala?
Yes.
So we have to use this line to calculate IC. Okay. And we have to calculate that IC value when your BCB is equals to 10. BCB equals to 10 is here. Can you see?
Yes.
So always draw. First, I draw the line for IE, sorry, not IC, IE, and then you have to draw a line for VCB equals to 10. Where these two lines cut each other, that point will represents the IC. If you see at this point, the IC value is how much at this particular point? That is 3 milliampere. Understood or not? Should I
Yes.
explain it again?
No, no, it's clear.
I have to. Are you clear now? So first you
Yes.
have to choose IE value, then you have to choose VC value. Just draw a line like this where this cutting each other. You have to draw a parallel line and to find the value of IC from there. Right? Right,
Yes.
Kala? Okay. Just try to do the second question. B part and just tell me. B part.
Okay.
What he is saying?
It's still 3.
It's still 3. Okay, we reduced it to 2. So 2 will be
For
lying here
PCB.
somewhere here.
Yes.
Yeah. And draw a parallel line like this. And I is how much? I is
It's
remain
still
3 milliampere. Yeah. So that is again going to be 3 milliampere, right? Very
yes.
good. Next question. Next question. Can you tell me how we can solve it?
I think it's still 4. Because how can I
It's
find the
how much?
VBA? I have VCB and the IC.
Right. So what we can do now, Anna? VCB we know and IC we know. From these two values, we can calculate first IE.
Yes.
Okay.
Yeah.
So from this one, IC is equals to 4 milliampere. Just mark that one.
Yeah.
This line represents IC is equals to 4 milliampere, and VCB is equals to 20. That means this
20.
line will represent. So they will intersect here. So I is how
4,
much? Can you tell me?
4 milliampere.
Very good. Now back here into the first graph, because on this graph we can see the VBE,
Oh, okay.
right, Bala?
Yes.
And you have to make IE. IE is how much which we calculate from the second graph,
4.
that is 4. So just draw the line like this, 4 at 4 milliampere. Understood?
Yes.
At VCB is equals to 20, it means which graph we have to follow? This graph we have to follow. So what you are seeing, they will intersect with each other here, and you have to calculate that value. It's just above 0.7. This is
0.7.
0.7 here, Gala?
Yes.
Yeah, 0.7 point something, 2, 3 like that. Something like that. It's just above the 0.7. Did you understand or no? Tell me that, how
Yes.
we can do this.
Yes.
Should I
So first
explain it again or every?
no, it's clear.
Yes.
We find the IC, then sorry, the IE, then we go to the other graph. Same thing.
Yes, you have to do, because he may bring this type of question with you.
Yes.
Okay, next question. This is common emitter configuration. So inside the common emitter configuration, what is happening? You have to remember this configuration, right? Which is the input output like that, right? Then you will easily understand the things. So inside the common emitter configuration, so basically this is our emitter terminal, right, Vala? And this is your output terminal. This is RC. So we are taking the output here at RC, VCE, VCB, sorry, VBE. This is VBE. This is RB this time. This is your base terminal. This is emitter. This is collector. Did you see this? Can you see this circuit?
Yes.
So inside this circuit, what you are seeing, the input current, see, basically this is IE, this is IB, and this is our IC, right? Like this. Sorry,
Yes.
IC is coming in like this. Yeah. So what is the input current and voltage? Input current and input voltage.
The
Can you
input
tell
is
me?
the input is VBA and the output is VCE.
Very good. So VB input voltage and current is input current is what?
IC.
That is IB, input current.
Input, sorry. IB.
Right. Okay. Tell me the output current and output voltage.
VCE and IC.
Yeah, VCE and IC. So this is your output characteristics, and this will be your input characteristic. Can you tell me what is the current gain here? Output current, that is IC upon IB. Output current upon input current.
Isn't it IC over IE?
What you are saying?
Isn't it IC over IE, the alpha?
No. In this case, see, basically you have to check that input current and input voltage. Oh, sorry, input current and output current, right? So inside this circuit, what is the input current? Input current, can you tell me?
IB.
Just see the circuit. Yeah, this is the input. So always remember, whenever you defined any type of gain, either you are defining input gain, current gain, voltage gain, power gain, always remember the gain is what? Output upon
Output
input.
over input.
Right. So basically, if I define the current gain here, right, if I define the current gain here, so the output is what? Output current is what? Because we are defining the gain, current gain, right?
Yes.
Current gain. So we have to use the output current. That output current is IC, right, Kala? And input terminal is this one. This one is the
Yeah.
input terminal. So input current is IB. Did you understand now or no? Tell me.
Yes.
So this current gain in this case is output current upon input current, and that will be represented by beta. Got it or not?
Yes.
This this beta represents the current gain of which configuration?
Common
Emitter.
common emitter.
Because the emitter terminal
Yeah,
is
the
common
E
in
is
between
in
the
between.
input and output. Right, Gana?
Yes.
Right. And always remember, the value of beta is very, very greater than 1. Value of beta is lying between 15 to 900, like that, right? Always, it is always greater than 1. So beta is very high. You can see here. Okay, now back to this one. So this is our current gain, beta. You can see the beta, right? IC upon IB. Its value is very high. Generally, beta is 150, like that. It is very high value. Okay, one more thing. These are the output characters. Should I explain it again, or you understand everything here? These are the similar one. Just the change of values. Inside this one, we have VC. I already told you. IC here
Yes.
in the output characteristic, input characteristic, VB and IB. No need to explain this one, or need to
No.
explain?
No. No. I got this.
Right. Mm, yes. Okay. I already told you that there are inside the semiconductor, there are two things. One is majority carrier, another one is minority carrier, right?
Yes.
So inside the transistor, there is another current that is called as minority carrier. Generally, we can neglect that. So if we consider that current, that is ICBO, this current is called as minority carrier current. So basically, the minority carrier current is what? That is very
ICBO.
small, and we can neglect
Yeah.
that. ICBO. And there is a relation between ICEO and ICBO. This is the relation, it is important, right? This relation is important. Sometime he may ask you the question. So you should remember this relation, and always remember ICBO is the minority carrier current. Right, Kala? Okay, this is not important. Okay, tell me now. See, basically, if I talk about the beta, what is the formula for beta?
Um. Here it's IC over IB.
IB. Right, that is for DC. If you are calculating for beta AC, that will be change in output current upon change in base current, right?
Yeah.
Right. Okay. So if I calculate the this beta DC, we calculate this beta DC at this Q point. How we can calculate? So you have to calculate the value of IC and IB. So at this Q point, what is the value of IC? Just draw a line here. How much is IC? That is 2.7 something. Can you see this or not?
Almost the 3 years.
Yeah, that is below 3, 2.7 like that. And how much is the IB? That is 25 micro. So you can calculate beta DC, right? If you are calculating beta AC, so you need two values of IB and IC. So let us take the first value of IC is here and second value of IC is here. So that is 3.2, another value is 2.2, right? So change in IC, because beta IC, what we defined? Delta IC over delta IB, right?
Yes.
So delta IC means change in current, collector current. That is 3.2. Above one minus the below one is 2.2 divided by change in base current. So first current is 30 microampere here and minus 20 microampere here. 10 raised to power minus 6 and that will be 10 raised to power minus 3. So that is your beta AC. Did you understand these two things or no? Tell me now. That is easy.
Yes.
That is the way how you can calculate the beta value. Yeah. Do you have the formula sheet which is given to you in your exam?
I think yes, because he gave us in the quiz, so he will give it to us.
Explain this how we can do.
Huh? We multiply the beta with the 1, so beta equals to alpha over.
Let me tell you that IE is equals to what? IC plus IB.
Yes.
Okay. And alpha is equals to how much? IC over IE.
Yes.
And beta is equals to how much? IC over IB.
IB.
Very good. So from these equations, from this first equation, if I calculate the value of IE, that will be IC over alpha. And from this equation, if I calculate the value of IB, that will be IC upon beta. And I plug in this value into this equation, the first equation. So IE can be replaced by IC upon alpha is equals to IC as it is, and plus the IB can be replaced upon IC upon beta. So IC we can take the common from the right hand side. If you take the IC out, that will be 1 upon 1 plus beta. So this IC will cancel out. So what we got, 1 upon alpha is equals to, when you take the LCM, that is become beta and this is beta plus 1. Now reverse this one, alpha is going to be beta upon beta plus 1. So this is the relation between alpha and beta. Right, Gala?
Yes.
So from this relation, if you multiply this 1 beta in here, alpha beta plus 1 is equals to beta, then it is become alpha beta plus alpha is equals to beta. Take this one into other side. So alpha is going to be beta minus alpha beta. And you can take the beta out. So the beta is 1 minus alpha is equals to alpha. So the beta is going to be alpha upon 1 minus alpha. So this is important relation. This one and this one. Understood?
Yes.
Okay, let us move. So the last configuration is common collector configuration. Inside the common collector configuration, what is happening? So your collector terminal is common. Collector terminal is common. Generally, we will give the input to the base. And we are taking output at the emitter terminal. So this is VCE, RE, emitter terminal is here, and collector is common. We are giving the input at the base. So this is your VCB, right, like this. So in this case, input characteristics you can check. So input characteristic can be drawn in with respect to what? Can you tell me? Input. IB is the current input and VCB, right? So
Yes.
that will be
And the output is
IB,
the VCE. I see.
VCE, IB. Sorry, IE, not IC. IE this time, because common terminal is here, collector terminal is
Yeah.
common.
Sorry.
That is IE.
IE.
Understood or
Yes, yes.
not? Current gain of this configuration is how much? Output current is IE and input current is IB. So this is represented by comma. I think it is not represented here. Comma is not defined in this case, right? Okay. These are the characteristics. Should I explain this or no need to explain this one? This is the same. The lower one is cutoff region, this one is the saturation region, and this one is the active region. These characteristics are same, just value will be changed here, here, and this one. The characteristics will remain same, right?
Yes.
Okay. One more thing. The power dissipated in each configuration. Common base configuration, power is what? VCB means power means at the output terminal. So basically, if you remember in the common base, what is the output side? In the common base configuration, what is the output side, Kala?
VCB. The IC.
VCB and IC.
Yeah.
So what will be the output power? Power is always current into voltage.
Yes.
VCB into IC. Can you see this?
I
In the second case, common emitter configuration, what is the output current and output voltage? Output current is
IC and VCE. Yes.
IC. And in the common collector configuration, VC into IC. That will be the power.
Okay.
And this, I don't think this table is important for this exam, right? But you have to memorize this table. This is not have no explanation till now. We will explain it later when we do the next chapter, chapter 5. Then we will define everything, that dynamic resistance, current gain, voltage gain, power gain, everything about these transistors in the next two chapters, right? So that is having no such importance here. Okay. Okay. Back to this question. So configuration is easy to find.
Yes. The common emitter configuration.
Common emitter configuration. What he is saying, that IB is 35 microampere and VC is equals to
10
10
volts.
volt. 10 volt and 35 microampere. So basically what is happening here, we have to check that where they will lie. IB is 35 microampere. So this is 30 and this is 40. So you have to draw a line in between these two like this. Right, Gala? In the center of this one.
Yes.
Let's take this line represents 35 microampere. And at what value of VCB?
At 10.
10. So just draw a line of 10 here.
Yes.
So they will intersect, I think, here at this point. So this line represents your current. That is 3.8 milliampere. Did you understand or no? Tell me, Gala.
Yes, yes. It's the same way we did the other side.
That 3.8 milliampere. Understood?
Yes.
Should I move to the next part?
Yeah, the only difference we added another line between 40 and 30.
Yes. Because that is not given. So we can
Yeah.
think that it will be at the center of this one, right?
Yes.
Next is what?
VCE is 0.25 volts. IC is
And IC is?
6 milliampere.
So you have to find the region of operation of the transistor. Okay. 0.25. Can you see here? That is 0.5. That is 2.5 here. So 0.25 must be lie here or not? Can you tell me?
Yes.
So that will be 6 here like this. So it will lie in which region? Can you tell me? I already told you there are 3 regions. So this region is saturation region.
Yeah.
Understood, Gala?
Isn't
Or
it the
should I
active
explain this one?
region?
No. Why?
Or
You have to
maybe
check now what is the
yeah, I drew the line like not very straight. That's
what is
why.
the that is VCE. VCE is how much?
0.25. So yeah, saturation region.
0. Yes, 0.25. So 0.25 means, see, this is 5, 2.5 at the center, 2.5. So almost one box represents how many volts? There is 5 boxes inside each one. From here to here, there are 5 boxes. So 5, 2.5 divided by 5. So that means around 0.5 volt. Each box represents 0.5 volt, right? So it means there is 0.5 here. So 0.25 will be lying here in between these two like this, right? So it will be lying here. So 0.25 will lie in saturation region, right? That is, it means it is saturation. Understood this question or no? Tell me that.
Yes.
1 second. I will take. Do you have the true false or not?
Which one? There are many
For
olds.
this exam.
Oh yes, I have this page.
Right? This page. Okay. The 10th question is what? Can you read it? The 10th from the last.
In the cutoff region, the base emitter and the collector base junctions are a transistor are both reverse bias.
It is true or false? Just memorize that table, right? That is
The
really
cutoff
important.
region, yes, it's true.
Yeah, both the junctions are reverse bias, right? Just read
Yes.
just about this one. Read the 9th.
Saturation region.
Yes. Base emitter junction is forward bias, whereas the collector base junction is reverse bias. Check it. What are the condition for saturation region?
No, both should be forward. False.
It will be false, right?
Yes.
8th question.
Yes, IE is always the largest current. No,
See,
but
read
the
this one.
collector is not the always small. The
Not
base.
small. See, I already, yes, base current is small. So remember that 1000, right?
Yes.
Base is
Yes.
100 and the collector is 900,
900.
right? That will be easy. So that means, yes, that will be false, right?
Yes.
Okay, read the first part, first question. So what is beta? Beta is basically what? IC upon IB.
Yes.
And I already told you that beta is always greater than 50 and around very high value. So that means it is true. Understood or not? Tell me that one.
Yes.
Okay, next, second question. Read it and tell me. Second.
The alpha is IC over IE.
Very good. And its value is how much? That is almost equals to 1.
Yeah. So true.
0.99, something like that. True. Third. Third question. Can you read it?
Yes, in the active region, the base emitter and collector base junctions are forward bias. False.
Very good. Why?
Active region, forward bias and reverse bias. The
Yes. Base emitter junction forward bias, collector base junction should be reverse bias,
reverse
right?
bias. Yes.
So that's what we studied today, right? Understood or not?
Yes.
Okay, one thing left. And day after tomorrow you have the exam? Or tomorrow?
Thursday.
Day after tomorrow, right?
Yes.
Now the last question we will left with the operating limits of the transistor, how we can decide that, right?
Yes.
And this question is in the exam, I think so. Okay. See, basically, every transistor has its maximum power rating, PC maximum, that how much maximum power it can handle. Right, Gala? How
Yes.
much maximum power it can handle. And that will be specified here. So this transistor can be handled that much power. So this PD maximum is given here, that is 625 millivolt. Right, Gala? So
Yeah.
that the maximum power, how much this transistor can be operated, that is 625 millivolt. Understood or not?
Yes.
And this is represents derate derate factor, you can say. Derate factor means what? Whenever you increase the temperature above 25 degree, whenever you increase the temperature above 25 degree, then its power dissipation, or you can say the maximum power will degrade. Every 1 degree rise in temperature, 5 millivolt it will degrade. So if I ask you that you have to calculate it at 30 degrees centigrade, so how much is this one? So if I increase the temperature 1 degree, so the power will be degraded by 5 degree, sorry, 5 millivolt. It means at 30 degree, how much power will be less from this one? Did you understand my point or
30.5.
not?
Yes.
So that means how much temperature I increase from 25? That is 5 degree. From 25 to 30, how much temperature I increase?
150.
No, you didn't understand what I'm saying. I'm again repeating. See, basically, transistor has one property. Maximum power dissipation means what? Did you understand what
625
is
milliwatts. Yes.
625 millivolt? It means that much maximum power it can be tolerated by the transistor. If you increase the power dissipation by this transistor above this one, your transistor will be burned out. It can
Okay.
handle maximum 625 millivolt power, right? This power rating of the transistor will decrease with increasing the temperature. If you increase the temperature by 1 degree above 25, it means if you reaches to 26 degree temperature, then its power rating will be decreased to 625 minus 5, that is 620 millivolt. Understood, Ghala, or no? Tell me that one.
Okay.
He's saying that when you increase the temperature above 25, its power dissipation decrease at a rate of 5 milliwatt per degree. As you increase the temperature 1 degree, its power dissipation decrease by 5 milliwatt. Let us take you increase the temperature to 30 degree. Right, Gala? From
Yes.
25, you increase the temperature to 30 degree. So how much temperature we increased? 5 degree?
600. No. Yes, 5
5
degrees.
degree. So it means the power become how much? 625 minus
And
5 into 5. So that is
600.
600 milliwatt. Got my point? If I take
Yes.
this temperature to 55 degree, then how much power dissipation will be? 625. Oh, sorry, 625 minus how much temperature we increased? Can you tell me, Gala, how much temperature we increased from 25 to 55?
30.
30. So 625 minus 30 into 5.
5.
So it is become how much? 150. So 625 minus 150, how much is this?
475.
Milliwatt. Did you understand or not? Tell me that. How, if I increase the temperature, the power dissipation will decrease inside the transistor? I think that question is asking at 55, right? Your exam question.
Yes, at 55.
Yes. So first step is what? We have to decide that how much power dissipation should be there. The power dissipation is 475 milliwatt. Okay, Ghala, or not? Tell me that thing. Did you understand how I decide this or not?
Yes, yes.
So always remember, you have to check that the temperature, how much temperature is above 25, and you can use this factor. Maybe inside the different table it will given you different. So just focus on this thing. Okay. Another thing is common emitter voltage, VCE. Common emitter voltage that can be maximum handle, that is 30 volt. So VCE maximum is how much? That is 30 volt here, right? Got it, Lana, or no? Oh, sorry, Ghala. Did you understand this one or not?
Can you please repeat this? The
Right.
PCE?
Yes. So VCE is what? Collector to emitter voltage.
Yes.
So collector to emitter voltage rating. See here, these are the maximum ratings. Maximum rating means how much collector to emitter voltage it can be operated. So the maximum voltage will be 30 volt. So VCE max is how much? Gala, that is 30 volt, right? And
Yes.
now IC max, collector current, maximum collector current is how much? Can you read it? The collector current maximum. Can you see here? Collector current IC, that will be 200
200.
milliampere. Did you understand how I got these values or not?
Yes.
Now what I have to do, we have to find the shape operation of the transistor from this specification sheet. So first step is what? You have to draw the characteristics look like this one. So on this axis we have VCE, on this axis we have IC. Right, Gala?
Yes.
So the first step is what? You have to draw the maximum value. See, what is the VC? What is the VC as the maximum value? VC max. That is 30 volt, right?
Yes.
And IC max is how much? That is
200.
200 milliampere. So the power dissipation is equals to what? IC into VC, if you remember that formula.
Yes.
So first, whenever your current is maximum, we have to calculate the VCE. So power dissipation is how much we calculated here? That is
400,
475, right?
yeah.
Is equals to IC maximum is 200. So VCE. So VCE value corresponding to this how much? That is 475 divided by 200. Can you tell me how much is this? 475 divided by 200.
2.375.
2.375. So that means that will be lie here. 2.375. The first point. Understood or not? This is our first point. Okay. Then we have to decide whenever you have 30 volt, how much is the IC? So the power dissipation again is what? IC into VCE. So this time you have to use the VC value. Power dissipation is 475. We have to calculate IC, and whenever your VC is equals to 30 volt. So IC is how much? That is 475 divided by 30. Can you tell me how much is this IC? So we have to drive these points. I am telling you how we can drive these points. Right? Can you tell me how much 475 divided by 30?
15.84.
15.84,
Yes,
right?
yes.
Right. This is our second point. Right, Kala? Now, you have to choose any two values, two or three values between 2.3 and 30 volt, right? You can choose any two, three values and just find at that values of VCE, you have to find the IC. You can choose any two or three values between 2.3 and 30 volt, right? Let us take, I choose 20 volt, right? So at 20 volt, you have to calculate the IC. So IC is power dissipation upon 20 volt, right? So IC is how much? 475 divided by 20. Can you tell me how much is this IC?
23.75.
23.75. So mark that point here. Right? 23.75 like this. That this. Another point, let us take at 10. Right? So IC at 10 is how much? That is PD over 10. 475 over 10. That is 47.5. So we will mark that point also there, 47.5. Then match these points like this. So this is your shape operation of the transistor, the region of shape operation. That is. Understood, Gala, or no? Tell me that. Or should I explain it again?
Yes, clear. Do I have to?
This is your exam question.
So this.
Check that.
Can I ask you about the drawing? Do I have to like write each region, like which region is active, saturation, the cutoff, or
no.
doesn't work?
For this one, no need to write it. Just draw it like this. Right?
Okay.
That's it. I already solved one question. Don't if you remember, I already solved one question in the assignment for this one.
Yes, yes.
Right? I already solved. How much marks you got in the both assignments?
Both are 5 out of 5.
4 point?
No, both are full marks. 5 out of
Both
5.
are full marks.
Yes.
Very good. Good. And what about your signal yes, DSP assignments?
The first one was 8.9 and the second one is 9.25. But I changed the course. I am taking it with another professor.
Okay. Okay, now you understand this question or not? Just check
Yes.
that question also, right? From the assignment. I solved there, right? You can check there and solve that question by yourself. Okay, that's it from my side, right? If you want any other help in any chapter, you can come to me. I will teach you that one also, right?
Okay.
Any doubt in this chapter you may ask.
No, that's it. Thank you.
Right.
Maybe
Just
I will be
revi
sending you tomorrow the exam. I will solve it by myself so you can correct me if there is anything wrong.
right, right. No worry. Just send it to me, right?
Oh,
Okay, Gala.
thank you so much.
Welcome. Good night.
Thank you. You too.
Bye bye.